If in case you would not like to appear in the video or in the recording, kindly turn your camera off. So my name is Zach Shureb-Conti, and I'm a research associate at the Alan Turing Institute in London, although I'm currently talking to you from sunny Malta, which is my home country. I would also like to introduce my colleagues and co-organizers, Andrea Pizzoferrato, who is an assistant professor at the University of Bath, and also Temis Botsas, who is also a research associate at the Alan Turing Institute. So for those of you who are not familiar with the Alan Turing Institute, this is UK's National Institute for Data Science and AI. Also, for the benefit of those joining us for the very first time, I'd simply like to sort of very quickly introduce the topic of our bi-monthly series, and that is physics-enhanced machine learning for engineering applications. Physics-enhanced machine learning is an upcoming subfield in machine learning and deep learning that aims to integrate known physical understanding of observed phenomenon into the machine learning framework. And of course, advantages include data efficiency and interpretability of the prediction models, which are vital criteria for real-world engineering applications. And as I said earlier, if any of you are interested in sharing your work in this field with us and with the community, kindly get in touch for us to schedule a seminar slot. As for the format of this seminar, our speaker will first talk for around 30 to 40 minutes, followed by a Q&A session. And the questions may be asked in person by raising your hand in the Zoom function, or if you would not like to appear, you may also type in the question in the chat, and I will, of course, relegate to our guest speaker today. All right, so without further ado, I'll ask my colleague Temis to introduce our speaker for today. And with that, I thank you all so much for joining.
Thank you, Zach. Thank you, everyone, for tuning in. Our speaker for today is Professor Subramanian Ramamoorthy. He has a PhD in electrical and computer engineering from the University of Texas. He has been an elected member of the Youth Academy of Scotland at the Royal Society of Edinburgh. Also a visiting professor at Stanford University and the University of Rome La Sapienza. He is currently a professor and chair of robot learning and autonomy within the School of Informatics at the University of Edinburgh. He is also a Turing Fellow. And in addition, he is a vice president of prediction and planning at 5AI, which is a startup focused on developing technology for autonomous vehicles. Today, he's going to talk to us about system identification from sensory signals. Thank you very much, Professor, and the floor is yours.
Thank you. Let me share my screen. Are we looking at the right screen?
Yes.
Okay, excellent. Firstly, thanks to the organizers for having me. I think this is a very important area. It's very timely, so I'm very happy to be part of the seminar series. I'm happy to see many new names in the list. It would have been many new faces if they had been in person. So I want to talk to you today about a topic that has been kind of emerging in my research group for a few years now. And I struggled to find a title that would convey exactly what I wanted to say. And I never could find exactly the right title because all of the terms that I use in the title could be misconstrued in terms of very traditional concepts, whereas we mean probably something slightly different with the terminology. So the way my talk will go is I'll first introduce the problem a little bit, and I'll slowly ease into what we mean by physics in the physics-informed machine learning. So by the end of the talk, I'll talk about a problem that is well and truly physics and chemistry, whereas in the early part, you will see me talk much more about robotics problems and the difficulties that come when one is thinking about model learning, real-time estimation, world understanding, and so on and so forth. So with that, let me jump in. A lot of the work that I'm going to talk about today had its beginnings as part of a Turing-sponsored project. So I'm a Turing Fellow, and I'm part of the AI program. And so for the past 3 years nearly, I've been working in this area that we call safe AI in surgical assistance. So it began as a collaboration with a couple of medical colleagues of mine here in Edinburgh. And the genesis for us was we were thinking about what would it take for us to take robotics technology, which has made rapid advances in the past decade or two. I mean, like significantly so, even in my short career. And what would it take for us to bridge the gaps from going from there to it actually being usable in the sense of some degree of autonomy in the operating theater? So there's a lot of robotics that's used all over the world, but we are asking questions about autonomy. So this led us to ask a number of different questions. So one category of questions we were interested in is, can we learn models of what's happening in the environment, what's being shown to us by demonstration, and so on? And can we learn models in such a way that they are structured for interpretability purposes, which is something that was mentioned in the introduction, but also structured from the point of view of us being able to do analysis. So uncertainty quantification is one example. Having some idea of, I've learned this model, what do I expect in terms of extrapolation properties or, out of domain generalization and things like that. And the long-term view is that, if you can learn good models like this, then you can also perhaps do better in terms of getting guarantees in the control synthesis side. So for us, this is a full loop. And those of you who work in robotics, engineering, control systems, you'll be very familiar with the general loop I'm talking about, of course, and you will realize that these are long-standing big problems. So what I'm going to do is to give you glimpses from a few different projects that touch upon the theme of physics-informed machine learning, but also in the process make certain commitments about how we might go about structuring, designing, and doing learning algorithms. So to make things a little bit more concrete, here's one example that came out of our work in the past couple of years. So the task that the robot is performing here is to excise grapefruit. Now the task is motivated by the long-term view that one day we want robots to pick up a scalpel and excise tumor. But of course, I mean, that takes a long time to get towards. So we started out with something that doesn't look that far away when you think in terms of consistency and properties, which is other biological soft tissue that we can manipulate. Now, this is a day-to-day task. Even if you haven't done robotics, you've probably done this task somewhere. You've probably used a knife and scooped out some fruit or meat. What's going on here that's interesting is that the robot it can only go so far with vision or any external kind of perception. So you look at this piece of fruit, you can't tell me exactly where the boundary between the peel and the pulp would be, and how exactly you should move the knife to get it. So much of the information that you want is coming indirectly from the force measurements. So you're going from how does the knife feel when I go through it? If I'm going through the pulp, it feels like it's going quicker. If I'm going through the peel, then it feels harder. And in many ways, the control strategy you want is to glide at that interface between pulp and peel, and that would be the perfect excision. And the machine learning and the engineering problem we want is how do you solve that inverse problem going from this very indirect measurement of what the forces feel like on your wrist all the way to this is the 3D structure and then kind of correlating it with other things. So this is a small glimpse of what actually is a much bigger problem in the real world, but it motivates the kinds of things that we might be thinking about. Now, there's actually a much broader range of such learning problems in robotics. So inverse problems are everywhere, even though it doesn't always appear in the way that engineers would think about inverse problems. So I give you two different examples here. In the top pair of images, what you see is a human demonstrator demonstrating how to perform a reasonably complex task for robots, which is identify and pick up Lego blocks, put them together, do the force control to get them assembled. And you see that on the right side, the robot actually learned how to do it from watching the human do it. The inverse problem here is that the actual signal you get is just a video stream with not too much interpretation. So the inverse problem is all of the things about what were you paying attention to, how did you move, what was the control strategy you were adopting, because it's really the controller that you want to transfer onto a robot from human demonstration. And what you see at the bottom is a different kind of problem in which the robot is trying to do intention-aware assistance. So it's really performing a sequence of physical tasks, but the sequence is tightly coupled with what the person is trying to do, both at the level of where is he moving and how exactly is he moving, but also in terms of logical states about when do they switch from one thing to the other. So in some sense, when I use the term inverse problem, I refer to all of these. It could be soft matter viscosity kind of prediction. It could be at the level of intention prediction. And to us, they're all kind of similar problems. And likewise, when I use the term physics inspired, I want to refer both to physics in the kind of traditional sense, like continuum mechanics might be physics, but I also mean, the like switching processes, H&Ms, decisional processes, all of them are in some sense to us a representative of the kind of structure that we want to bring into the machine learning pipeline. So with that preamble, let me jump into the first project, which will show you this idea of, what do we want to incorporate in the sense of structure when it comes to movement strategies. So a movement strategy, such as in my previous slide, when the robot was kind of doing assembly and assistance and so on, and where the movement strategy has some hybrid switching nature. So you have both hybrid switching in the sense of logical switching between different modes. And then you also have continuous dynamics underneath, which is the controllers. So to make it very concrete and keep it simple for visualization, consider a simple inspection task that's kind of been made quite elementary for the purposes of illustration. So you have 5 blocks on the table. The robot has been given an inspection task in that it has to go from one block to the other in a sequence. So it involves continuous dynamics in that it's doing visual servoing to get to one block. Once it has got there, then it gets a signal, it goes to the next block, it goes to the next block, and so on. So there's the identification of the actual movement, which is physical movement. And then there's the identification of the state machine that's sitting on top. Now one could, and so the whole point, what makes this interesting is that this is not given to us in terms of a state machine or a differential equation. It's given to us in terms of video. And we are being told, copy this behavior, right? And so if we just applied kind of standard, whatever is your favorite end-to-end approach, with deep learning or optimization-based synthesis and so on, it would be quite hard to solve this problem upfront without any other bias, because you have somewhat non-trivial switching structure, even though the images are clean and it looks kind of tame. Now, in robotics and thinking about robot control, these kinds of tasks have been thought about for a long period of time, and this comes under the umbrella of thinking about compositionality, where a single visual servoing controller is one entity, and then you're composing on top of that so that you have a switching structure with all of this. What we are asking is, how do you invert this? And we want to invert this in such a way that we understand the structure so that we can make changes to the structure later on, change the inspection order, add objects, and so on and so forth. Now, one could take a fairly conventional view. I'm trained as an electrical engineer and I'm familiar with a whole bunch of kind of estimation techniques. You might have your favorite thing, but there's basically a statistical toolbox of thinking about, inferring these kinds of models. And one approach might be to say that we're going to learn a switching model sitting on top of something like these proportional control laws. So if you're a physicist, think about this as an attractor with a basin of attraction going to a point. If you're a control theorist, think about this as your standard proportional control architecture in one form or the other. And then the statistical inference problem might be, if you did it that way, that you learn this kind of a switching model. I'm not saying we do this, but this is one framing of how you could do this. The reason I'm not saying we just do it as a statistics inference problem is that if you're going to do it directly from high dimensional noisy images, then it tends to be really difficult to get any of these algorithms to work well. And the only ones you will get to work would be extremely expensive in terms of Monte Carlo simulation and so on. So what might be other alternatives? So I'm going to begin with one alternative and I'm going to refine it later. So the first kind of basic thing you could do is to say, I've been given data, and the data I've been given is a person performing this task and us taking video clips of it. So you get a sequence of images of what the task looks like. So one approach might be that you begin by training a model, in this case, a deep neural network model, that is not capable enough to learn the full task, but it can learn sort of local predictions about, if this were the input image, what would I expect to see in terms of movement? And you could train such a network. And then you could perform sensitivity analysis on the outputs of this network. in order to then do real-time inference to say, based on this model, which I'm using as a process model for local prediction, I can extract that what the robot seems to be doing is to go towards this object and then to this object and so on and so forth. And so this pipeline, if you implemented it, might look like this. So what you see here is the video data that the robot is kind of looking at. And through the process model that I'm describing, it's kind of changing its beliefs about, in terms of particle filters, what is the most likely object that the robot is moving towards. If you had an idea of that, then that allows you to abstract from the continuous motion estimation to the symbolic state machine estimation, which gives us a sequence such as this. So you go from raw pixels as you've been watching it to a sequence of images that tells us that this was the sequence of blocks it was visiting, from which you can use a variety of different automata learning methods to actually learn a program. Right? So this is one approach to solving an inversion problem. It's a useful approach, and we've kind of deliberately shown you an example in which we've kind of abstracted the problem to just show you the essential elements, but each piece of this can be made more complex as we wish. Now, what does this allow us to do? So this allows us to look at a sequence of demonstrations such as that Lego assembly that you saw earlier. And it allows us to break it down in the sense of model learning and inversion into a sequence of high-level transitions between low-level controllers. And we've done this by doing inference on sensitivity of local prediction models. And then what we've really done is to learn a vocabulary and a program on top of it, where the vocabulary amounts to going above the tower is a small sub-movement, closing the gripper is a sub-movement, and then it's a program in terms of this. So when you then execute it on the robot, what it does is it firstly learns how to execute the state machine as you taught it, and then the fact that the low level is a continuous controller gives it robustness with respect to noise, and the high level state machine gives it the structural bias that we want it to have. And then you can also tune different parts of it. For instance, you can retrain one of the local pieces to have coordinate invariance such that if I turned the whole scene a different way, then it would still execute the same program, right? So this is what we mean by structured models. This is great. And this was our first attempt at this problem. And it was interesting from the point of view of giving us a highly explainable approach to doing model learning. But then we started asking ourselves, there are many moving pieces here. So I haven't just given you one solution and said, look, I can solve the problem. There were many moving pieces. And there were also some very interesting choices that you might not have picked up on if you weren't paying close attention, such as that I said every elementary kind of block, every controller is essentially an attractor. What if you somehow needed a repeller at some point? What if you needed some other kind of low-level objects? So there's actually a desire to take this kind of structuring approach, but then come closer to the ways in which we think about end-to-end learning and to think about inductive biases in different ways. So this led us to our second attempt at this problem. And so in our second attempt, we still go from pixels. We still have the same problem of kind of visiting a number of different places. But then we started asking ourselves, could there be an integrated neural network architecture that somehow captures both the switching dynamics and the local dynamics, right? So the local dynamics is an attractor or a proportional controller, depending on your favorite speak. And what we want is for it to naturally capture switching. Now, one might hypothesize that, hey, there are kind of architectures out there going way back to the 90s. There are architectures like mixed density networks. Could we use them? It seems to have this idea of multiple components. The answer is not quite, because mixed density networks are nice as a statistical object, but they're not doing what we are asking for. They don't cluster and kind of talk about meaningful components and then talk about switching. What they're really doing is averaging. So they were designed for a different purpose, although they look seductively useful. So what we did was take inspiration from that and try to modify it. And our modification is what we call a switching density network. So it begins similarly to a mixed density network. It goes from pixels and it goes through a sequence of visual layers. What's interesting is what has been added on the output layer, which involves a Gumbel softmax and then a collection of different distributions, each associated with one of the modes that the Gumbel softmax outputs. Now, if you're not familiar with Gumbel softmax, it's essentially a modification of softmax in a function that looks like this. The salient thing to understand is that depending on how you set the temperature parameter, this approaches switching. So in the way that you train these kinds of networks, you can introduce annealing along with backprop so that you can get switching out of this. And what we're really interested in predicting with this kind of a network are the parameters that go into a controller architecture, and there'll be one each for each of the modes, so that depending on which object you're going for, it switches naturally. So there's one big neural network that now incorporates both the continuous dynamics and the logical dynamics. And so this is what this gives us. If we perform the same kind of inference from watching what people were doing, with a switching density network, we cleanly get the switch between the different modes. So this is time, and these are the modes. So we see that as the person is performing the inspection, the network picks up the logical structure, whereas a mixed density network would have just given us some average notion of movement. And locally, of course, it also learns exactly how to move. And so this can be applied to a number of different problems. We can apply it to continuous controllers with switching structure. We can apply it to robotics problems with kind of discrete contacts and different forms of switching based on that. And the main takeaway from this first section is that we are interested in coming up with ways in which we can embed hierarchy in the sense of hybrid control into a neural network for the purposes of interpretability. What we find is that when you have tasks that naturally have the switching structure, we get a significant boost in performance. And when you have tasks where the switching structure is not quite so salient, we do slightly worse, mostly because of numerical issues in training, but no worse than with any other architecture we would have used. So we would present this as an approach to thinking about incorporating the possibility of learning structure. So this is project number one. And in fact, this project is part of an agenda of a team for us in our group where we did a number of different works, which all had this idea of somehow taking a programmatic description of what we think would be a high-level structure for a decision and allowing neural networks to be good where they are in dealing with the perception components, and then somehow combining them. I'm not going to describe this project. I'm simply saying that there's a very general template for thinking about these kinds of problems. Now, if you come from a different community and if you're familiar with physics-informed neural networks in the sense of a number of different groups around the world, you might notice that in that setup, this program gets replaced by equations of motion, such as Navier-Stokes. And it looks remarkably similar to like a PINN when you think about the ways in which we are incorporating structure. So it's a fairly general template that we like quite a bit. Now I'm going to switch gears and I'm going to come closer to the ways in which other people sometimes refer to the term physics-informed machine learning. And here we're going to ask the question, how do we incorporate physical principles directly into the video prediction loop? So here we are talking now about integrated neural network architectures that are taking raw signals such as videos, and they're trying to make predictions about the future. And we're asking, how do you start incorporating physics into this loop? It's motivated by a number of different cognitive science principles. A lot of people around the world have made the observation that people are remarkably adept at picking up physical properties from very little data. So here are two videos that are just meant to evoke the idea that there's a lot going on in human cognition about our ability to learn, what must be the mass and spring constant of this object, what must be the relative mass between green and the colored block that's falling down. From a single snapshot or a single video clip, we're able to make estimations like this. And that gives us spectacular skills when you look at what people can do. So when we learn sports like this, from a single throw, fractions of a second, you're able to figure out what is the speed, what is the spin, what should you expect in the future, and so on. So for us as roboticists, we were interested in, is it possible for us to do that with a robot? So exactly the same catching problem. What we want the robot to do is to look with its video input. And we wanted to make a prediction. So if a ball is thrown from this side and it doesn't get any visual of the ball on this side, can it make a prediction based on the history that's observed from this section for where the ball is going to end up here so that it can catch it, right? So it's a simple kind of problem made to illustrate the point we want to make, which is about the possibility of the robot having good physics predictions. So it's not just predicting video forward, it's making predictions with respect to physical parameters. And the way we go about it, now here I'm going to show you the architectural principles. Clearly with a presentation like this, if you want all of the details, you should go read the paper. But let me first tell you what the architectural idea is. So we start with a variational autoencoder architecture, which takes an input and it tries to reconstruct the exact same input by going through a bottleneck layer in a neural network. So that's the starting point. What we would like to be able to do in terms of physics informed is we want to put in physical equations of motion, in this case that of a ball, drag, restitution factor, rolling, friction, all of these. We want to put them in the form of data that's coming out of a simulator that is an ODE solver output of this into the latent space of the variational autoencoder. Now, of course, we don't just want one snapshot of the latent space, we want dynamics in the latent space, which means we have to add one more component, which will be a recurrent neural network that modifies the state in this latent space. So we're going to put these three principles together and make an architecture. So we're going to have an architecture that injects knowledge by doing a reconstruction loss as in a VAE, a sequential loss as in recurrent neural networks, and a simulator loss, which gives us the physics informedness. And if you train a neural network with all of these, then we will show that it's actually able to learn behavior such as this. So to show you in graphical terms what's going on in this architecture, we start with the VAE block. So you have an input, you're trying to reconstruct that input by going through an encoder layer and a decoder layer. And the latent space Z is meant to have what we would have written down as equations of motion. Whereas the input variable is really just raw pixels. It doesn't have any interpretation yet. Now, normally in a variational autoencoder, you would essentially say that you want this to be some kind of uniform Gaussian so that you can learn distances between attributes. And then you would use the encoder and the decoder as a way to get in and out of that latent space. So that's the reconstruction part of it. We train a recurrent neural network architecture so that we can predict dynamics in this space. So it would take what's here, and then it would learn how to roll it forward based on the training data. So it would take what is in this space, and then it learns how to predict forward. And then we do one more thing in addition to augmenting it with this hidden variable, which is that we train a network that tells us what to expect in the latent space because of the dynamics of the recurrent neural network. So there's a variational autoencoder, there's a recurrent neural network. The recurrent neural network does forward in the latent space. We take that step forward and we put it back into the latent space of the VAE, right? And so if you do that, what you get is you get the ability to predict forward based on what's going on in the latent space. And then you also get the ability to train this whole architecture from time series data of what has actually been observed. And then the last bit in all of this is to add the loss term that tells us that whatever is going on here in terms of dynamics, in terms of the updating of this probability distribution, must be compatible with our physics equations of motion. In this case, they're not terribly complicated physics, but they're complicated enough that video prediction done naively doesn't actually perform that well. So if you put all of these together, you get the loss function, the details of which I'm not going to go into all of the equations here, but to say that this is the architecture with which we are making predictions. So what this is allow us to do, so the first outcome, of course, is that this allows us to perform system identification in the sense that the ball is thrown, you have a week prior about what the properties are when it's thrown, and as it is bouncing towards you, you update the parameters and you have a much better estimate of what has happened, right? And so that's what we are showing here for different parameters. What's worth noting is that some things are easier to pick up than others. So the coefficient of restitution is easy to pick up as soon as you see a bounce. But something like drag is incredibly hard to pick up because not a whole lot of drag going on when you just throw a ball. And it's also hard to disambiguate between the gravity and drag and things like that. But the point that's being made here is that to the extent that it is possible to disambiguate, these kinds of models are learning pretty well. And they do much better than alternatives, which include performing Bayesian optimization over the parameters of the physics model, or sampling and taking a least squares fit to the best possible parameters. So doing this kind of an architecture outperforms it in terms of accuracy. It outperforms it in terms of evaluation time. So it actually performs much better in terms of the amount of time it takes to make a prediction, because really the forward pass of a neural network. And it also performs better in the sense of unseen forward prediction. So if you're looking forward in time and asking, where do I expect the ball to be? Our approach, which is in blue, performs much better in comparison to a number of other alternatives, which include the approach of kind of estimating parameters by a Bayesian optimization procedure, doing some kind of an SVD to the signal, DMD to the signal that we've seen so far, and then projecting forward and so on. So these are kind of baselines that one might take as standard in the literature and see if we are doing better. So what else can we do with this? We perform an experiment in which we, after periods of time, we change the parameters. So for instance, the coefficient of restitution changes from 0 to a higher value and back. Gravity changes from different values. These are all in synthetic experiments, of course. And so on. And what we see is that depending on the level of excitation of the system, meaning depending on there must be some distinguishability in the process, the model is able to actually keep up with some of the changes, while for some changes, it's very hard for the model to actually pick it up. And then we move from this on to sensitivity analysis to make the point that there's a reasonable amount of noise robustness. So we can change many of the underlying parameters by up to 10% before the error actually creeps up. We can change sort of, different parameter values. And also, if we dropped out a few terms in our simulation models, which is what we call reduced versus full, then the behavior is still qualitatively similar, although the more physical terms that we can incorporate, the better the quality of reconstruction would be. So these are all done on synthetic data. And then we perform similar experiments moving forward with physical data. So here we've trained on synthetic images with a lot of data augmentation. And then we are testing on real tennis balls and ping pong balls and stuff like that. And what you can see is the ability of this model to have seen a snippet of the trajectory in blue and then predict forward in red, and then comparing that with gray in ground truth. And our approach in terms of time and quality of reconstruction performs better than some other sampling-based alternatives. And this is what it looks like when you look at it in real performance. So what you're seeing here is a ball being thrown, and as the ball is bouncing, you see the model update its predictions about what's going to happen in the future. And then when it goes behind one of these obstacles, it has to make the prediction blind and then act on the basis of that, which is our way of testing, has this actually meaningfully learned these parameters. Now, of course, this is an incredibly difficult task for a not very fast moving robot, but it performs better than some fairly simple baselines that you might adopt, which suggests actually that the prediction bit is happening just fine. You need to do more to on the control side if you actually want to reliably catch the ball. And I want to highlight a few more things. In the way that we ran these experiments, we not only changed physical parameters about the ball and so on, we also changed parameters such as what if the robot has an initially bad estimate about the height of the table, environmental factors, can it actually catch up to that? And the answer is yes, it figures out how to kind of cope with those kinds of changes. So what I've shown you in this subsection is the ability to do system identification in the sense of online estimation of physical parameters by using a variational recurrent neural network with a latent space that has been modified to encode physics. Because there's a forward pass of a neural network, it is actually pretty fast in the sense of online estimation. And to a certain extent, it's able to cope with noise, variation in parameters, unknown dynamics, and so on, which are important issues in many of our use cases. Now, I would like to move to the third section. In the third section, we want to do exactly the same thing as you've seen with the bouncing ball, except we want to address a somewhat more complex physical phenomenon. And now we are in the territory of, if you were coming from physics or chemistry, this would be hopefully what you would call genuinely as complex physics. So what we are interested in here is to do very similar kind of problem as the previous one, except the dynamics is that of molecules. So we are interested in the temporal evolution of these molecules that are going to be observed through X-ray scattering. So the setup here is that these molecules are going to be excited by an optical laser. So they're going to be pinged. This is the equivalent of me perturbing a ball. And then in response to that, they're going to oscillate and exhibit dynamics, which then gets observed by X-rays, which are the second thing that are sent after the first one. And then the scattering from these X-rays is observed on a detector. And what we are interested in, the observational signal, is the profile on this detector. So what you see here is the radial signal as you're looking at one of these radial axes. So it's symmetrical, so you're only really interested in one axis. And so from time instant 0 to time instant 2, you see the radial signal change, which tells you that the image is changing because of the movement of the molecule. Now, the underlying physics is determined by a functional such as this. So the underlying physics is based on a couple of different factors. We're not going to go into it, and I'm certainly not the best expert to kind of talk about the intricacies of this. But to give you an idea of what's going on, there's a probability distribution function that refers to pairs of electrons and where we expect to find them. There's a function that corresponds to the molecular geometry. And then there are terms pertaining to, how many electrons there are and what is the underlying structure of the molecule, right? And taken together, this gives us a function. And what we are really doing is to observe this function, which is our indirect signal, and inverting back to what is the geometry. That's what we're trying to estimate. So what's going on is the equivalent of the bouncing ball here is a bouncing molecule, which is giving us an observed signal. And we're asking, can we go back? While it is possible for some very small molecules to perform the forward calculation, it is already quite hard and computationally it's quite expensive. And certainly inversion is not only expensive, but also has ill closeness. So we take exactly the same architecture I've shown you before. And so we are interested in using an encoder-decoder architecture where the latent space is meant to capture the essence of what we think is the dynamics of this molecule. We have a recurrent neural network that's telling us, so the variational autoencoder is telling us what is the latent space. The recurrent neural network is telling us what is the dynamics. And then by using this to modify the prior, we are able to get kind of forward predictions from this molecule, and we can perform learning and inference on the basis of that. And the physics bias is coming from the fact that we actually have ground truth data from molecular dynamics simulations that tells us what is the geometry and what is the observed signal on the basis of that geometry. So if you perform the same kind of learning, what seems to be done in this field conventionally when one is trying to evaluate algorithms like this is that one takes the observed output, traces of the observed outputs. Imagine that it's just like an image. You find the nearest neighbor image to that, and then you try to see if you can use the corresponding molecular geometry for that as a proxy. That's one way in which people have kind of approached this problem, which we can use as a baseline. And then we can measure the quality of geometry prediction in terms of mean squared distance and sum of squared residuals. So what does this allow us to do? So what are we looking at in terms of the outcomes of these predictions? Here we are looking at a time series of interatomic distances for specific types of molecules and then specific atoms in that molecule. As it's kind of bouncing around, you take two of them and say, how did they actually move with respect to each other? And then here you see a time series that's produced by ground truth, the baseline, as I said, in terms of nearest neighbors, and then our width to param architecture. And what you find is that, for heavy enough atoms, it's the equivalent of a ball that's properly heavy and is bouncing, and you can very quickly tell what's going on. All of these methods perform pretty well. As you look at somewhat lighter atoms where the intrinsic noise of what's going on is kind of overshadowing what you might get in terms of scattering. You find that the baseline methods don't perform quite so well, whereas width to param still gives you plausible outcomes. And then by the time we go to light atoms in different kinds of molecules, you find that we actually do better as compared to the baseline, even though we kind of have similar kind of incoming information. And here's experimental data presented differently. So for different molecules, you're looking at the cumulative RMSD of the predictions, where you're looking at predicted minus ground truth and then summing it over all time and trajectories. And the asterisk is meant to say that if there are additional things going on, such as dissociation, we are not actually taking those trajectories. So here we're just doing the bouncing ball prediction on the molecules. So what this has given us is the ability to go from what's going on in terms of the dynamics to what we expect in terms of the dynamics of the observation, and then do inversion. Now, what we've shown you so far are data in terms of, did it actually predict how this molecule is moving with respect to this atom is moving with respect to this atom kind of information. You could also have asked the question, if I just look at generated forward predicted observations and then actual observations, how does it perform? And that's what this trace is trying to tell us. And interestingly enough, what we find, kind of looking past the nitty-gritty of the numbers, what we find is that our procedure is doing better in terms of RMSD prediction of the actual structure than it is in terms of predicting what should be the observational data that's coming out on the detector. And this has probably quite a bit to do with the fact that there are more complexities and limitations in what the detector detects in the first place. So more is needed in order to exactly replicate that. But the architecture is actually doing a reasonably good job of getting us what we care about, which is the structure of the molecule. And if you're interested in this, I would suggest going to this website where you can look at some of the data and interrogate this a little bit more. So what I've shown you are kind of glimpses through different architectures, different ways in which we've thought about incorporating physics. The need for us to incorporate physics is that we are interested in autonomous systems, closed loop systems, and all of them are tightly dependent on inverting measurements as a means of being more intelligent in the autonomy. So we're looking at lots of different problems which have the same kinds of structures. So I'm giving you glimpses of some projects that I'm currently quite excited about. So we're doing some work, which also came out of my Turing project, on trying to look at ways in which people do ultrasound scanning, looking for kind of deformities, let's say bone fracture or something like that. And what we want to do is to go directly from the raw images we get to kind of attributes of interest. So now the physics is both the scattering physics of what's going on inside, but also the mechanisms for how experts search and whether we can learn something from that. We are beginning to do work on kind of simulations in the sense of continuum physics and whether we can apply similar principles to that. And the project that I'm actually quite excited about is we're looking at in quite a bit of detail, what do people do? In this case, these are surgical trainees who are trying to take phantom tissue and show us exactly how they cut. And we want to understand in quite a bit of detail what they're doing, because if we one day want to have a robot perform surgery autonomously, it needs models like this. And so we're interested in being able to extract this kind of data. So to conclude, there are many ways and needs for incorporating physics as inductive bias. So I've shown you kind of two ways. One, which had to do with structuring the network. This was like the switching density network approach, where we thought about what kind of structure could you put in. And the second has more to do with, it's still structuring the network, but also thinking quite a bit about what kind of data you could feed it and how you can bring the pieces together. And then there are a number of issues that are arising in the specific applications I've talked about. So this ranges from switching and programmatic structure to the need for fast online inference. So quite a bit of other physics-informed machine learning that I have seen is interested in very accurately mimicking physics in a simulator, but you have the privilege of a lot of data and a lot of time, whereas here we are interested in real-time uses as well. And I'm quite excited by the number of different applications that this enables. And I should conclude by saying I'm very open to collaborating both with people who are working on problems like this and people who might have new ideas on methods like this. I think this is a very exciting time to be working in this general area, and I'm very happy and eager to engage with the community. So with that, I will stop speaking. I'll stop sharing my slides so I can see people, and I'm very open for questions and discussion.
Thank you very much. Thank you very much, Ram, for that very intriguing presentation, and thank you for sharing your work. So if anybody would like to ask questions, as I mentioned earlier, you may do so by raising your hand in the Zoom function. I believe it's in the chat section. Alternatively, you may type the question in the chat box. I guess in the meantime, whilst some are thinking of their questions, I'd like to ask a question, I guess overall discussion question. I guess the way first of all, thank you for showing. It's great to see yet again, you know, another way of integrating physics into the machine learning framework. And as we're seeing over the course of this series, we're seeing different ways of doing so, and how these ways are actually improving interpretability and also data efficiency of these models. And I think that there are, of course, review papers on these methods, but I think there is need of, you know, a really good review paper that covers in a very strategic way these ways of structuring this marriage. So one particular subsection in this field that intrigues me is universalization of these models. And I believe that, well, actually the question should go to you. Do you think that, you know, if we improve the way we structure and represent the structure of physics in these frameworks, we can actually come to a point where we can universalize these models? And how do you see this in the context of your research?
Right. And can I ask, so by universalization, do you mean kind of changing boundary conditions?
Yes, for example, learning learning the full differential equation.
Right. Yeah, so I actually do agree. In fact, I have been thinking along similar lines. I think, so we've been doing a number of projects. So in one of the projects, we are taking a simulator like NVIDIA Flex, and we're asking, can we make predictions? And the answer is yes, we can make predictions, but sometimes we ask ourselves, what's the point? Somebody wrote a nice simulator in the first place. And slowly we are coming to the realization that the point may be very similar to language models, which is that what we want is some generality to the object that we've learned. So I don't want a specific fluid under a specific boundary condition and a specific data set, and that's all I can predict. What I want is to be able to say fluid, and then what happens if I kind of, you know, interact with it in this way. And in that sense, I think that would be a very natural and fruitful direction to go. And I think there's plenty that we can bring from the rest of machine learning to bear on that problem.
Yeah, and I mean, for what you've shown us with regards to the bouncing ball example and the way it captures, you know, new sort of control parameters where you sort of change the environment and so on, I think that's get heading in sort of that direction, you know, where you to come to a point where you universalize eventually, because it learns, you know, the whole problem. Does anybody have any pressing question?
Maybe I can ask again another general question. So thank you, Ron, for your talk. So in general, I think it is possible to include physics in a machine learning model, maybe either as initial conditions, or also because, okay, we are saying that for whatever is the phenomenon is about, at least we expect the most simple behavior to follow the physical equation. But on the other side, I think physics can also be included as an upper bound and a lower bound. For instance, the ball that is bouncing cannot go beyond the speed of light. Maybe in general, we would like to do a combination of these two approaches, but do you have any preference to, even if you have to choose between either doing upper bound or lower bound, or embedding the physics as initial conditions, which one of the two do you think would work better?
Yeah, it's a good question. To be honest, I don't have a strong view on one versus the other. And in those situations, I try not to choose. It becomes problem by problem. My gut feel is that it depends on what aspect of the physics you want to embody. So if what you want to embody is the equivalent of conservation principles, I mean, so we don't actually see Hamiltonian systems, but let's say you wanted to say energy is conserved. There's simply no way to do it unless you put it into the architecture and say energy is conserved. I want this equation of motion, right? But there might be other things that are more like asserts in coding. That's what you mean by, you know, a ball that's bouncing with friction and restitution can't possibly go at a higher height than the previous one. So that's more like a filter. So I think it depends on what it is we are trying to embody. I would expect actually that both should feature, and it might become more like a, you know, it's like architectural principles and these things that you have, you know, certain blocks for this and certain blocks for this, and then you're trying to ask which one you want to put in.
Thanks.
Right.
Yeah, because yeah, sometimes I think about this, and for instance, I mean, embedding physics is some sort of supervised learning. So okay, like for applications in classical mechanics, then we know that, I mean, classical mechanics is it's very well understood. But I was thinking also about using these methods for new physics, and in that case, embedding some supervision could actually be a bias towards discovery new physics using all these new algorithms. So
yeah,
it's yeah, definitely. Thank you for the answer.
I would say actually one question. I don't have terribly clever ideas on this beyond what others have, but one question I often think, so what is the benefit of physics is something I think about a lot, because I mean, there's so much that's been done in physics, and in what sense is it general? And the answer is sometimes that, you know, we understand that, you know, if you make the right coordinate transformation, if you have the right Lagrangian, everything is this equation of motion. That is really powerful, right? So if you can embed physics at the structural level and say, I don't know anything about the parameters, but I know it must have the structural property. You know, it must have only one equilibrium point, or it must be a stable attractor. That would be really neat, because it's very hard to build other architectures that can capture that. But it's also, to be honest, very hard to represent this in the first place, right? So we've done work before the deep learning era. We did some work on topological data analysis and things like that. And they give you really powerful ways of talking about topology without commitment to any parameters. But there's no clean way to bring that in and kind of marry it, although people are trying.
Okay.
Extremely intriguing intriguing topic. All right, if there are no further questions, then I guess we can call it a day and let you go peacefully.
Thank you very much. Thank you for having me.
Thank you for joining us once again, and thanks for your time. No. And good afternoon to everyone, and thanks again for joining. We'll see you next time.
Bye.
Bye.